Well, thank you very much for the invitation. It's a pleasure to be in St. Petersburg. So I'll give a colloquium, like a very kind of general talk. So first of all, I would like to tell you a little bit about what rigidity is, or rigidity in the holomorphic category, the Kähler category, and the first theorem of this form is actually due to Calabi and Vecentini, or independently under Vey, which I didn't write there, I should have written there, 1960, which states that if you have compact quotients of irreducible bounded symmetric domains in Cn, when n is greater than 2, then those admit no infinitesimal holomorphic deformations. So you can deform those in the holomorphic category. And so another way to say this is if you have if you have a symmetric space M of non-compact type, which is Kähler, which this is uniformized by D, the disk in Cn. So if M is D divided by gamma, where gamma is the fundamental group, then those are rigid. Okay, so this is the first type of this theorem that I would like to talk about. This was kind of taken over by the theorem of Mostow and Modern Prasad. I added Modern Prasad because they proved the non-compact version of Mostow rigidity. And if you have two complete finite volume hyperbolic manifolds of dimension greater than 3, then if you have if they're homotopy equivalent, then if you have a homotopy equivalence between them, then this map F is homotopic to an isometry. Now that implies, for example, if you have in particular, it's a holomorphic. If those are complex symmetric spaces, then they're going to be biholomorphic. So Mostow's theorem supersedes the other theorem of Calabi-Vecentini, and so it's worth thinking about that the deformation space of a complete finite volume. So we're interested in the space of the deformation space of complete finite volume hyperbolic metrics, and we assumed actually that the dimension is greater than 3 because as everybody knows, for n equals 2, in other words, if you're in the surface case, then they're completely non-rigid. In particular, if you look at hyperbolic metrics correspond to complex structures in the surface, and then there is a whole modular space, like as known by Riemann, 3G minus 3 dimensional space, and a complex 3G minus 3 or 3G minus 3 plus p the number of marked points. So the assumption n is greater than 3 is necessary, as the example of the modular of curve shows. Okay, so the space is completely non-rigid, even infinitesimally. So because I'm going to talk about Teichmüller space later, and so it's worth at this point even introducing the Teichmüller space. So we start with a compact Riemann surface of genus G, and p distinguished points. And then you look at the space of hyperbolic metrics, or the space of metrics of constant curvature minus 1. And on that space, you have the diffeomorphism group, the full diffeomorphism group acting, orientation preserving. And the quotient is the modular of curves, which is a quasi-projective variety. Now, if you mode out the space of Betrix by the smaller subgroup, in other words, the diffeomorphisms homotopic to the identity, then you get a Teichmüller space, and the Teichmüller space is by Teichmüller's theorem is homeomorphic to an open ball, actually in R 6g minus 6 plus 2p, or in other words, C to the 3g minus 3 plus p. So it's very similar. The situation is analogous to the Calabi-Vesentini version, to the symmetric domain somehow. So the Teichmüller space should be thought of as some kind of version. Actually, a lot of properties of Teichmüller space should be thought of as like analogs of bounded symmetric domains. Anyway, so we'll think of the Teichmüller space as bounded symmetric domain, and the fundamental and a mapping class group, which is the group of you take all diffeomorphisms and you divide out by the diffeomorphism homotopic to the identity, then acts on the Teichmüller space. And again, the quotient is the modulo of curves. Okay, so this is exactly the analog I had before. D, so Teichmüller space is the D, and the mapping class group here is the group gamma, and then the quotient here is the MG, and in here case is the symmetric, the locally symmetric space. Okay, so this is somehow the analogy we can think of. We'll come back to this later. So the question is, so most of rigidity was about hyperbolic manifolds. So the question was, does rigidity in some form hold for other manifolds than hyperbolic? And Yao in the 70s made this conjecture that rigidity of the holomorphic structure, the complex structure, holds for compact Kähler manifolds of complex dimension at least 2 with non-negative sectional curvature. Let me just see what this conjecture is. This says that if you have M, actually maybe it's in my next slide. Yeah, in my next slide is actually Siu's theorem, which almost settled the conjecture, and I'll say exactly why almost. So this is the holomorphic rigidity for compact Kähler manifolds. Is you start with one compact Kähler manifold. I guess I'm assuming that people know what Kähler is, or should I define it? It's a complex manifold where a Kähler manifold is a complex manifold where the associated symplectic form is closed. The associated form. So if you have a G. The J is the complex structure, and then there is omega and then you have this form. This is a Hermitian metric. This is a complex structure, integrable complex structure, and then you have this condition. So if you have so the main example actually for this talk is if we have a projective variety. A projective variety inside CPN is always, if you have a projective variety, it's always a Kähler manifold, because you can pull back the Fubini-Stodi metric or the standard symplectic form or the standard metric from here. You can pull it back there on the manifold M, and that defines it like a Kähler structure. So projective varieties are the main examples, or some of the main examples of Kähler manifolds. But anyway, so you can think of this term as projective variety. So anyway, you have a compact Kähler manifold. You have two compact Kähler manifolds where I'm putting no assumption on, I guess Siu put no assumption on the first, but on the second manifold he assumed that it has a negative curvature. This condition, we'll come back to this in a minute. It's the most naive, Yao conjecture this in the case where just the sectional curvature of the target is negative or non-positive. But but so there is a slight notion of a stronger version, and actually there are no known examples as of this point of manifolds who admit a negative curvature, sectional curvature, and do not admit negative curvature in the sense of the stronger sense. So it's very hard to find examples of manifolds which are of negative sectional curvature. We don't satisfy this assumption. And certainly all the examples that we have in mind, like symmetric spaces or Teichmüller space, all those spaces satisfy the stronger assumption, which I'm going to define in a little bit. So anyway, if such things, one of them is negatively curved, then if you fix a homotopy class, then there's a holomorphic map in this homotopy class. Now, in other words, in the homotopy class of maps, there's a holomorphic map, which in many cases is biholomorphic. So in other words, it settles the question that we have two manifolds, out of which one is strongly negatively curved, and they're homotopic, then they're biholomorphic. So this was kind of a breakthrough due to Siu. At this about 9080, yeah. Here's the definition of strong non-positive curvature. So this R alpha, beta, gamma, delta, bar. That's the curvature. This is the curvature tensor of the metric. And then we're assuming that this tensor has this positivity, because I put the minus sign there in front of there, has this positivity property, or otherwise without the sign it's negative. And this is a general. I mean, this is stronger than the notion of negative sectional curvature. For example, if I take this C alpha to be A alpha conjugate and D beta B beta conjugate, then you get this non-positive sectional curvature. You see, so this is more. So usually the non-positive sectional curvature is only along this tensor is negative along certain planes. Here we're assuming more parameters there. So anyway, for now, actually the way Siu came up with this is because we'll see it pops up this condition, pops out of his when he was trying to prove this theorem. I'll say a little bit more about this. Okay. Any questions? So anyway.
Sorry for a naive question. So, is there some way to describe manifolds of strong negative curvature with some intrinsic, well, I don't know, not intrinsic, but on the contrary, some like classification?
I mean, actually, what I was saying before is that it's very hard to find examples of manifolds, of non-positive, in other words, all the manifolds that you're interested in, like symmetric spaces, Teichmüller space, satisfies this stronger assumption. So it's hard to find natural examples which do not satisfy this and have non-positive sectional curvature.
I'm sorry. So you have, I would guess, the strong negative is a little bit stronger than strong non-positive.
Strong negative.
It looks strange.
Hang on a second.
You want strong positive, maybe.
Yes, maybe
not.
I think the upper.
Let's see. Maybe I messed up.
Doesn't match with the bottom line.
Non-positive. Sorry. I think it's a typo here. So it's non-positive. Okay. Yeah. I mean, so there's a so I have non-positive or non-negative if this is positive. Yeah. No, I think it's correct. Actually, is correct because you have this minus sign there.
Yes, but then after you have negative, then it should become positive, no?
Let's see. We see there.
If you change the sign.
non-positive becomes positive, and then, oh, sorry, I mean, this is a typo here. This is positive.
Okay.
Okay, it's a typo. It's positive, yeah.
Positive is respectively
Positive, no, not negative, respectively positive. Oh, sorry. So this is non-negative and this is positive.
Okay.
Okay, so I decided recently. I mean, so if you forget the minus sign there, means that this is non-positive or positive. Okay. So anyway, anyway, so. Okay, so, and again, as I said, this strengthens Mostov's theorem because we only need to assume that, for example, we can take the target only to be a symmetric space of non-compact type. The domain doesn't have to be a symmetric space. Okay, so in the process of proving this theorem, Siu introduced effective techniques to apply harmonic map theory to solve rigidity problems. So I'm going to describe a little bit about these techniques here. So if you have two Riemannian manifolds, let's forget Kähler now, just completely Riemannian manifolds, then and you have a smooth map between them. Then you could write the differential of the map, which one way to think about it is it's let me just write it here. So the differential du of x goes from a tangent. So I can think of it as a section of the cotangent bundle of M, actually I'm prime here. With tensor with a pullback of the tangent bundle of M prime, and local coordinates is du is given by this expression dui dx alpha ddui. So in local coordinates, where ddui are the coordinates of it's a local frame. ddui is the local frame induced on the pullback bundle by the coordinates of M prime. Okay, so and then you have the Riemannian metrics on the manifold induce metric on those bundles, and you just take the norm of those, and there it is. This. So and then you can integrate this. That's a Dirichlet energy. So over an open set U, you can integrate the energy, this energy density du square of x. And then this is the local energy on the set U, and the Euler-Lagrange equation is given by this equation dE star du equals 0. In other words, where dE is the connection. So in other words, this M prime has a Leibniz-Civita connection. So if we pull it back on this bundle, on this U star on Tm prime, so that's the connection on, this is the E, this is the pullback of the connection used by the Leibniz-Civita connection on M prime, and then if you write down the Euler-Lagrange equation, it's just d star du equals 0, where star is the adjoint, d star is the adjoint operator of dE, of the differential dE. Is that clear? So this is the harmonic map equation, actually. So this is one way to write it, the harmonic map equation. You can write it also in the local form, actually. So Laplacian, maybe you've seen this form, if U has coordinates ui, so we can write this as where these are the Christoffel symbols. So this is the Laplace-Beltrami operator in the domain, and these are the Christoffel symbols of the target. So this equation that I wrote there in this invariant form is equivalent in local coordinates to this harmonic map equation. Okay. Okay, so examples, if you have, so if your domain is S1, so harmonic maps are, so a harmonic map from S1 into M prime is if and only if it's a geodesic, so generalize the geodesic equation. And if M prime is the real line, then the harmonic map generalizes the notion of harmonic functions. So harmonic map is a notion that generalizes both the notion of geodesic and the notion of harmonic function. Other examples are minimal surfaces, totally geodesic maps. For example, if you have a map that sends geodesics to geodesics, then that's harmonic. Holomorphic map between Kähler manifolds are harmonic. And then I'm going to talk a little bit later about pluriharmonic. If you don't know, that's okay. I'll define it later. So these are examples of harmonic maps. So the first question is, so around 1963, Ilse and Samson proved the following theorem, that if the sectional curvature, just the sectional curvature of the target is non-positive, then in the case both of the manifolds are compact, then we obtain we have a harmonic map more or less unique in a homotopy class. In any homotopy class of maps contains more or less, up to more or less unique harmonic map. It's not really always unique up to some parallel translations, but anyway, it's more or less unique harmonic representative. It's a little bit like, you can think of it like as a nonlinear version of the Hodge theorem, for example, like you have a Hodge representative. In fact, the proof is exactly like a similar. Actually, the original proof of the Hodge, one of the proofs of the Hodge theorem is via the heat equation. So it's via the way Ilse and Samson proved this theorem, we prove it by generalizing the heat equation and show that this parabolic equation converges. So anyway, so if you follow like the proof, it's not much harder than that. It's a little bit harder than that, but not much harder to prove this existence theorem. But they also prove this following formula. The following formula that it's an example. It's called the Ilse-Samson-Bochner formula, which says that the Laplacian of the energy density is equal the Hessian, grad U squared is the Hessian, plus some term involving the Ricci tensor of the domain, plus minus a term involving the Riemannian curvature of the target. So, and actually the important thing is that these terms, for example, if we're assuming that the target is non-positively curved, so the second term is positive or non-negative. Now, if also this term, in other words, if also this term, the Ricci term is also non-negative, then what follows out of this is that the map is totally geodesic. So in other words, this is the first example where you see that out of a harmonic map, this example of rigidity that I was talking about, that a harmonic map, which always exists in the homotopy class, in other words, you have two manifolds that are homotopic, and let's say if you assume that the domain has non-negative Ricci curvature, then the map is homotopic to a totally geodesic map. Unfortunately, this assumption of a domain having non-negative Ricci curvature is very restrictive. For example, it's not satisfied by hyperbolic manifolds, what you're interested in. So this is not very useful for if you're interested in questions of rigidity. But nevertheless, it's the technique. Actually, introduced this technique, which this Bochner method on harmonic maps. Okay, so the way you prove this is the following. You have this equation, 1/2 Laplacian grad u square equals those terms. Now if you integrate this, so by Stokes' theorem, so let me write this down here. So if you integrate Laplacian on a compact manifold by Stokes' theorem, this is 0. And then you integrate the right-hand side, and all the elements and all the terms on the right-hand side are non-negative. So in particular, what you get that, for example, this equals this. In particular, you get this is how you prove that this map is hyperbola geodesic. Okay.
So I missed what have you explained there?
So I've explained why if you have so how do you prove the theorem that this last statement here, that if you have if R m prime is less or equal than 0, which is always true, I will assuming, but the reach is greater or equal than 0, then a harmonic map is totally geodesic. And the reason is just by Stokes' theorem, integrating. So integrate Stokes' theorem and then reprove it. So the lesson we learn from this is that he has to prove the right Bochner formula. So the story is he went and asked Calabi, and Calabi asked him to complete the square. At least that's what Siu tells me. Okay, and there he came up with the Siu Bochner formula, which I'm going to explain. Okay, so I actually, if you look through the proof, if you work out the proof, it's really completing the square somewhere. So anyway, so to describe the Siu Bochner formula, we have a Kähler manifold M prime. So we just take the pullback again like we did before, but now E is the pullback of this holomorphic tangent or this 1-0 tangent bundle. So in other words, you have the splitting of the tangent, the complexified tangent bundle splits as T10 of M plus T01 of M. So and then we can write down the derivative of u du. Actually, this is, I guess, prime. So du, which goes from T of M to T of M prime, we can complexify this. Look at the complexified map. And then we can split it into components, del u and d bar u. And then we have, and then you can take the pullback again as before of the complexified Levacivita connection on M prime. And this is decomposed as, again, 1-0 part and 0-1 part, del E and d bar E. Okay, so just decompose, in other words, the connection and the differential into type. And then, but then you have this bracket that if you have two forms, two PQ forms on E and psi and eta, then we define this bracket there, this psi eta. So what it does actually, you wedge the forms. So psi is E-valued PQ forms. So you wedge the forms with bar there, and then you use the metric to contract the frames on the M prime. Okay. So if you do that, then here is what he proved. He proved this is the Bochner formula that he was telling me it's completing the square. So if you have a harmonic map, and with omega is the Kähler form of M, RE is the curvature operator of the pullback bundle, and then we define this term. So omega. So if we get this this so then you have this term of r d bar u omega to the n over n factorial. You can write this as, you can write in other words the bracket of d bar u and r prime on d bar u as some function times the volume form. Okay, and the whole point is that if you look at, actually this is, if you look at this what comes up in this formula there, this is exactly that term that comes in the strong negative curvature. So in other words, if you compute dd bar of d bar u, and this is a very simple computation, it's not that hard. You just do choose normal coordinates on the metric and you do the computation there. So dd bar u, so you get this d prime du squared plus this curvature term there. And the curvature term is exactly this one that comes in the negative, in this definition of strong negative curvature. And the first term is the analog, is the complex Hessian. Is, remember, Il-Samson had the full Hessian, grad du, right, which implies totally geodesic. In there, you have this d e prime, d. Actually, there's no e prime, d e e. E. There's a typo there. d e of d bar u. Okay, and the solutions of this equation here is called pluriharmonic. This is what it means pluriharmonic. Equivalent means that if I take the d bar derivative of u, well, it's equivalent saying d bar e of del u. It's the same thing by taking bars. 0, and then so in particular it means that if we take the d derivative of u, then that map that form is holomorphic. It's holomorphic section of 1-0 forms. Okay, so again, so now if we go through, so here's the theorem then. So again, this is the definition of pluriharmonic that I said. So this is the equation. This is equation d bar e du is 0. So and another equivalent formulation is to show that if you take the restriction to any holomorphic submanifold, it's holomorphic. It's harmonic. So u restrict to any complex submanifold is holomorphic. This is equivalent to this condition here. So this is what it means to be pluriharmonic. So pluriharmonic is one step further from, it's not necessarily holomorphic yet. It's just the restriction to every holomorphic submanifold is harmonic. Okay, so it's something between harmonic and holomorphic. So we'll see holomorphicity. So now, so the theorem then he proves you, if you have a compact Kähler manifold, and the target has a strong non-positive curvature, and U is a harmonic map, then the map is pluriharmonic, but also we have this R of du is 0. This curvature term is 0 there. You must follow again the same technique, because you just integrate the dd bar u, you integrate the left hand side, and the right hand side has a sign. So both of them must be 0. So the first gives the pluriharmonicity equation. The second condition gives you that actually it's pretty easy to see that if the map has rank at least 3, yeah, so let me see if I say here, yeah. So if the map is rank at least 3, then it follows that d bar u must be 0, just because, and if the target has strictly negative curvature and the map is rank at least 3, then it must be holomorphic. So in other words, so you get the holomorphicity from the second term. So the map is holomorphic, and that's how so you prove this, in his case, the holomorphic rigidity theorem. Okay. Now I'm going to turn to So Siu applied this for Hermitian, for symmetric spaces. Now I was interested in seeing what happens for Teichmüller space, and I said Teichmüller spaces and symmetric spaces are philosophically very similar. So this is what the slide says, that the Teichmüller space, which is a disk, an open ball in C3G minus 3 plus number of marked points, and can be thought it's an analog of a symmetric space, or some sense. Okay, so here's I'm going to talk about the theorem. Some joint work with Chicago Messe. We proved that actually the holomorphic rigidity also holds for Teichmüller space. In other words, here's the theorem. It says that so consider the Teichmüller space of an oriented surface of genus G with p punctures, and gamma is the mapping class group. Now the theorem says that if gamma acts on a contractible manifold M tilde, and such that there is a finite index subgroup, such that if the quotient is a quasi-projective variety, then M tilde and M are equivalently biholomorphic. So I think I need to explain a little bit what, it's a little strange formulation of this theorem, but I'm just going to explain a little bit what this says. So the Teichmüller space, so the modular of curves, let's forget the functions. Let's say mg. Let G greater equal than 2. Let's forget the marked points for now. It doesn't matter. So mg is the Teichmüller space divided by the mapping class group. Let's call it gamma. And and this is homeomorphic to C 3G minus 3. So roughly speaking, we can think of this is the analog of M be some D over gamma, where pi 1 of M is gamma, right? So it's very analog. It's very analogous to this construction was described before with symmetric spaces. Now the problem with the Teichmüller space is the action of the mapping class group on the Teichmüller space is not free. So this is not an actual manifold, it's an orbifold. So you have to so either you have to use the orbifold, the language of orbifolds, like orbifold fundamental group or whatever, or for me, as more like interesting analysis, I pass to a finiteness subgroup gamma prime of gamma that acts freely on the Teichmüller space, and then I'm looking instead of a finite cover of the Teichmüller space. So this theorem is designed so this theorem says that if you have a gamma, if gamma, the mapping class group, acts on a contractible manifold M tilde. In other words, if you have a contractible manifold M tilde where gamma acts, and then such that there exists a finite index subgroup such that the quotient is a smooth quasi-projective variety, then actually these M tilde and M are equivalent biholomorphic, and therefore the quotients are biholomorphic. So it's a way of this. The statement here is a way of avoiding this orbifold language, but I could just state it as roughly speaking, as it's in other words, it's exactly the holomorphic. It's the analog of Siu's holomorphic rigidity. Instead of a symmetric space, I look at the Teichmüller space. Okay. Okay, so I have to tell you a little bit for Teichmüller space which metric I choose, and so I view Teichmüller space as hyperbolic structures divided by diffeomorphism, or diffeomorphism homotopic to the identity. And so the cotangent bundle of Teichmüller space is identified as quadratic holomorphic quadratic differentials, and there's a metric on the Teichmüller space. In other words, you have two quadratic differentials, H1 and H2, on the tangent space corresponding to the hyperbolic metric G. So then we define what's called the Weil-Petersson metric, which is phi psi bar dz bar over rho square. Rho is the conformal factor of the metric. So that's the Weil-Petersson metric, and the Weil-Petersson metric has some good properties, and it makes the Teichmüller space a Kähler manifold. That was proved by Alfors and Weil. It has is negative sectional curvature, proved by Tromba and Wohlberg. In the sense of Siu, that was proved by Schumacher. And the main problem, though, with Teichmüller space is incomplete. So there are no techniques to prove theorems for incomplete manifolds of rigidity theorems. So this is the main difficulty of the problem. So what do we do about this? Well, the way out of it, one obvious way actually is to take the Teichmüller space with the Weil-Petersson metric and take its completion. So in other words, you take the completion like the one you see in beginning real analysis, like take the space of Cauchy sequences, like the. Okay, we completed it, then we get a metric space, which is. But the problem then we kind of transfer the problem. We get a metric space, but which is actually turns out to be non-locally compact space, and also doesn't have geodesic extendability property. In other words, if you have the Teichmüller space is for example, geodesics make it stuck on the boundary, so it's like a manifold with boundary, in some sense. So it's a nasty space. However, because it's a completion of a space of negative curvature, is non-positively curved, and its boundary it's kind of understandable. In other words, the boundary of the Teichmüller space corresponds to lower dimensional Teichmüller spaces where each stratum is. So in other words, it's totally geodesic. In other words, the boundary is totally geodesic, and the boundary of the Teichmüller space consists of the modular spaces of nodal surfaces. It's like a cover in some sense. You can think of it as a cover of the Deligne-Mumford. So you have downstairs, you have the Deligne-Mumford compactification, and then this completion is what sits over the boundary of the Deligne-Mumford. Okay, so.
Can be described more or less explicitly for each particular case.
You see, for example, if you have, for example, the strata is you have this surface of genus 2, for example, then you start pinching curves. So the boundary would be, for example, the modular space or the Teichmüller space corresponding to this pinch surface. It's exactly, in other words, for any surface that appears the boundary of the module of curves, you look at the corresponding Teichmüller space, and you put all those together, you get this horrible, nasty space, and that's this.
At least there is a correct map. Yes.
There's a correct map. Yeah. There's a correct map. Yeah. But actually, a lot is lost in the map because the upstairs is not locally compact, and downstairs is a projective variety. So anyway, so this was conjecture of so going back to the conjecture. The conjecture is again the holomorphic rigidity so Jost and Yao made this. Oops. What is it? Yeah, Jost and Yao made this assumption that the quotient admits a structure of an algebraic variety with a codimension of the singular set that is 3. So in the conjecture. However, it turns out that you don't need this assumption. But that's a whole different story. I think I spoke in my seminar talk also a little bit about how to remove this assumption. But that's you have to use infinite energy maps, harmonic maps, to deal with this assumption, get rid of this assumption in their conjecture. So prove it the kind of more general version. But anyway, for now, I think we're going to assume at least that you construct. You can construct some. You have some finite. So in the problem you have. In other words, you have in the rigidity problems, if you have no two non-compact manifolds M and M prime, and you have a homotopy equivalence, at least you must have at least. It would be useful if you know there is a finite energy homotopy equivalence, and unless you assume this assumption, it's not known, or at least two. And maybe three is known, 2 is maybe true, but in general, if you have, there is no reason, if you have here an arbitrary quasi-projective variety, there is no reason why which is homotopy equivalent to the modulo of curves, there is no reason why this must have finite energy. Okay, but anyway, at this point, I mean, for this talk, we'll assume we're doing with the case that we have finite energy, so we can proceed with. So what we have to do in this case is we have to work equivalently upstairs on the Teichmüller space. So we have this universal cover, this contractible manifold, and we have this equivariant map F into the Teichmüller space, right? And actually, again, this T, we embed this into the completion, which is the reason is because this is complete, and actually, So this is a metric space. Again, I guess talking to St. Petersburg, I don't need to define, what a non-positive Xandrov is. So this space here is a metric space. dg bar is non-positively curved in the sense of Alexandrov. Okay, and for such spaces, Gromov and Schoen, and later extended by Korevar-Schoen, developed a nice theory of harmonic maps. So to deal, actually, their interest was in p-adic buildings. Completion of Teichmüller space is similar. It's very similar actually to p-adic buildings, and the theory, at least from the analytic point of view, the theory is very similar. Actually, in the proof of this theorem, we use a lot of these techniques that Gromov and Schoen developed to tackle the p-adic superrigidity theorem. So I'm just going to very quickly say what does it really mean to have a harmonic map in the case of a metric space. So if you have a complete metric space and a Riemannian manifold, and then some open domain there, and a map, then first of all we can define the notion of L2, meaning the distance square from U to some point is finite. It's the distance is integrable. It's in L2, and then maybe a way to think about it is that instead of you cannot define what the energy density is, but you could define what you can define what the gradient of a function is into a metric space, but you define what the gradient density is, and basically this is so first of all what you do is you take this approximate energy there, this u epsilon of x, which is basically replacing the gradient by difference of quotients, and then you take the limit as epsilon goes to 0 of this difference of quotients, and then you show that you say a function has finite energy or locally finite energy if this limit exists. Okay, so this is a way of generalizing what the energy density is in the case where the target is a metric space. So you could do that. And so this is a theorem of Korrevar-Schoen, extending theorem of Gromov-Schoen earlier, that says that this approximate energy density is converse actually to the energy density, and the energy density, if you're in a smooth case, is exactly what you're supposed to be. So the derivative, the norm of the derivative of u. So there's a way of. So in other words, I guess the only thing I would like you to have out of this discussion is there's a way to define an energy density in the case where the target is a metric space. So. Okay, so this is the definition of, I guess I was going to skip this. This is the definition of what it means for something, a complete metric space, to be NPC in the sense of Alexandrov, is if triangles are thinner than the corresponding triangles in hyperbolic space, right? If you think about in Euclidean space, something like this. If you look at comparison triangle like this. This is a triangle in this metric space, and we draw a same comparison triangle in Euclidean space. And if this is if this is thinner than this, then we say this is NPC, not positively curved. Okay. Anyway, so again we define harmonic. And we call harmonic in this case if it minimizes locally. In other words, there is no way to decrease it. So a map is called harmonic if it's local energy minimized. In other words, there is no other replacement I can do. So to make it to create a map of less energy. So this is what I mean by harmonic. It means locally energy minimizer. And again, let's give this. I'll skip these talks here. Oh, okay. So let's give the first bullet point. The second bullet point is that the first under the assumption of the theorem. First of all, you have a harmonic map. Remember, the first thing I said is use the Hill-Sampson theorem to show that in a homotopy class you have a harmonic map. Now, of course, you have a metric space, you have a complicated picture. So you have first of all to construct a harmonic map, and that's the first theorem that it's not terribly hard. That was done about 20 years ago by these authors, and then, so the first of all, there exists a harmonic map. Okay, so we have a harmonic map. So now we have the. So now we, as I said before, Schumacher proved that the Weil-Petersson metric is negatively curved. However, this harmonic map maps the domain into this horrible metric space, and unless I have some control of what happens, of what points map to what, then there is no hope of proving that, of using the Siu method. For example, if a whole bunch, if you have big sets mapping to the boundary of the Teichmüller space, then there is no hope of proving the theorem. So we make the following definition. We define the singular set of U is to set the points, the set of points that map into the boundary. Let's say to a single stratum. So in other words, you have the map from here into the completion. So here is to summarize. So you have a map. You start with a map F. Let's say fixed covariance class or fixed homotopy class into TG. So then you look at the map into TG, you view it as the map into TG bar, but then you construct a harmonic map, U. Unfortunately, the harmonic map doesn't map into TG. If it mapped into TG, it would be done. Because it's incomplete. What happens is when you start minimizing the map, it escapes to the boundary. The boundary is finite distance. So the map hits the boundary pretty quickly. So a priori, you have a map into TG bar. Right? And then what you would like to estimate is you want to estimate the singular set of U, which is all the points in the domain. so the map into the boundary. So you want to estimate this set of points, and so the theorem, the hard theorem to prove is the following, is that if you have a harmonic map from an n-dimensional Riemannian domain, this is a completely local problem. If the map is if it's harmonic, in other words, it's local energy minimizer, then it's only a small part of the set that maps to the boundary. Okay. I'm going to give a little example here. This is the really baby example. Let's see how I do with time. Okay, I'm done out of time, but this is okay. Let me finish, and then I'm going to give you an example of this.
You can go on 5 more minutes.
Okay, okay. I'll try to be quick here. So this is analog of this probably familiar picture. So what is an example of a harmonic map from between singular spaces, for example? What is the most simple example you could have? If you, for example, if you take a quadratic, if you take a surface S and take differential phi, but take the one z dz square, okay, this quadratic differential, then you have the leaf space of this quadratic differential. So it looks like, so if this quadratic differential has a simple zero, and its leaf structure looks like this, and you look at the map that maps into the leaf space. So in other words, all these leaves here, they're mapped to this. Okay, so this is the simplest example of a harmonic map that maps into a singular space. Okay, so this maps actually this tree here. Okay, I mean. So here's the point. So here is this definition of the singular set. So look, for example, a point here on the domain. So this point here. So what happens here locally, the map. So even if you change, you go across this singular leaf. But what happens here is that the map, actually a neighborhood of even of this point here, it maps. It's not very singular. It looks like a function. However, if you look at this point here, this is bad because there is no way to go. So some of the set goes into there, some of the sets go into there. So this is a singular point. However, you notice that the singular set, there's only in this is two-dimensional problem. So in 2 dimensions, the singular point is codimension 2. So this theorem is actually for Teichmüller. Actually, it turns out Gromov chain proved this is true for not just for trees; it's true for buildings. And actually, what we prove in this theorem, this is true also for Teichmüller space. In other words, if you look at the singular set, in other words, the points that map into this boundary, the bad points have codimension 2. Okay, so once you have this codimension 2, in fact, actually, so once you have this codimension 2, and then you got to also control what happens to the second derivative of u near the singular point. So you have to write a theorem like this as well. But once you have a kind of control of the size of the singular set, plus some good control of the Hessian of the second derivative of u near that point, then you can actually apply the Stokes theorem. The problem is that Stokes theorem, if that comes from Siu's formula, if you cannot control the singularities near the singular set, then gives boundaries, and then you can't get 0. But once you have this decay, then you can apply the Stokes theorem, and then actually again follow Siu's method and show that integrate by parts, and show the pluriharmonicity. So this is how the theorem is proved, and this is the heart of the theorem, which I didn't have. Let's see. Oops. I had time to describe. Right. This is the hard part of the theorem, that controlling the singularity set of the harmonic map, exactly like in this simple example there. So anyway, I was planning to say more about a little bit describe like why this is true. Actually, maybe one more since I was given the permission to do 5 more. I'll show you a little bit why this PDE is hard in the Teichmüller space. Oops, go backwards. I'll show you a little bit why this. Here is actually the harmonic map equation for or like a simple. This is how the harmonic map equation looks like in for the Weil-Petersson metric. It looks like this very degenerate partial differential equation. So some kind of again, I don't have time to explain it, but so u rho is so you can like so it looks like a function of two. So anyway, so it's a nonlinear differential equation where it involves this function u rho, that u rho goes to 0, so it's not an elliptic. It's a degenerate elliptic equation. It's not actually an elliptic equation near the singular set. So and that is the problem, how to deal with this differential equation, and so. But anyway, I'll stop here.
Thank you. Are there any questions?
Yeah, questions. So the question is general about these theorems. They're useful to compare manifolds, so like manifolds with negative curvature or something like that. And can you maybe show example when it helps really? So when you have to compare two manifolds, you don't know they are the same, but it helps in this case. So maybe for Teichmüller space, it was some motivation for you. So some example was motivating you for this theorem, or maybe for just manifolds with negative curvature.
So I guess in the rigidity question, you have. I mean, the motivation is to show that you have two. For example, if you have one motivation would be if you have two complex structures on a Teichmüller space, maybe someone can. I mean, and you wonder whether these are the same or not, right? So actually, this theorem says that if these complex structures come from a Kähler structure, right? It's important that those are Kähler manifolds. Then they must be the same. So
you mean that you can even apply it to the same manifold and
yeah.
So
Right. For example, suppose someone gives a construction of another Kähler metric on the Teichmüller space, or any other construction of a Kähler metric Teichmüller space, for example, and then this theorem will say that actually this is the same as the standard one, coming from Deligne Mumford or whatever, Alford Spears or whatever. All of these complex structures are the same. I'm not sure. I mean, I didn't say. I mean, this is one case. The other case actually, I stated only a special case of my theorem. The theorem also has to do with classification of surface vibrations. So, for example, in an application of this theorem says that if you have any topological surface vibration over a quasi-projective variety, it necessarily has a holomorphic structure. Mm-hmm. So that's provided that it says at least sufficiently large. So that would be that's another application. I mean, this is another application.
So do you think the base is sufficiently large?
Well, here it is. Actually, precise theorem is the following: if you have a quasi-projective variety, and you have a vibration f. Actually, let me state this because So if you have a quasi-projective variety of complex dimension n, and then say some even doesn't have to be complex. If it's some smooth actually 2n plus 2, a vibration by surface of genus G. Then what you could do is you could put a Riemannian metric here, and then given a Riemannian metric, this induces a conformal structure on the fiber. So then you have a classifying map M from M into the module of curves, basically mapping for every point X in here, right? You map this fiber, okay? So now over here, so if you look at this map then, U, F, now the condition is if this map is not homotopic to a map of rank less or equal than 2, which actually, for example, if F maps, for example, homology classes of three-dimensional homology classes and trivially to three-dimensional homology classes, we can check it on the basis of homology, then if you have, for example, if it's non-degenerate, then this map, you can construct a harmonic map, and then you can prove this map is holomorphic. So in particular, you can take the universal curve here and pull back under this holomorphic map, and this could be isomorphic to this vibration you started with. So in other words, an application is that any topological, it's very surprising, any topological vibration basically has it's a holomorphic vibration. So that's another application.
Are there any other questions? If not, then let's thank the speaker again.